So good evening, thank you for coming. I'd like to welcome fellows and visitors to this, the fourth discussion meeting of the current session. And I invite people to contribute to the discussion after the main presentation and the vote of thanks. If you do contribute, please be aware that the meeting is being filmed and it'll be posted on YouTube. If you don't want your part to be included, could you let us know at the end and we'll make sure you're edited out accordingly. So I now call on Professor Silverman to present his paper, Multiple Systems Analysis for the Quantification of Modern Slavery, Classical and Bayesian Approaches.
Thank you. The last time I read a paper was, I think, in 1990, and the previous time 85, and I'm every bit as, I feel just the same as I did then. So it's really great to be here, and thank you all for coming. What I'll say again, what's important about discussion is not the paper, but the topic, which is of enormous importance. The other thing is I'm told I'm not allowed to move around, so if I uncharacteristically stand still, you'll just have to get the excitement from my voice, because otherwise the camera won't work. So let's ask the question, what's modern slavery? Modern slavery encompasses many aspects of human trafficking and exploitation, and there are tens of millions of victims worldwide. And I've given some examples on the slide of the categories, the kinds of victims that there are. Our understanding of this phenomenon is actually not good at all. This is one way of categorizing things. You look at the different ways in which people are involved, and there's also that the Home Office has produced what the minister at the time called a typology of modern slavery, which is also very helpful. No country is free from modern slavery, we reckon, and there are two words, modern slavery and human trafficking, which are closely related and often used interchangeably. They're not quite the same thing. In the United States, they don't like the phrase modern slavery at all, and in this today, I'm not going to distinguish particularly between modern slavery and human trafficking, but they are highly overlapping, and maybe people who contribute to the discussion will say more about that. Why is prevalence estimation important? So I've produced two quotes. James Cockayne from the United Nations University, who works for a United Nations agency that works a great deal in this area, says, without good data on where slaves are, how they become slaves, and what happens to them, anti-slavery policy will remain guesswork. And that's what actually many of the early fellows of the Royal Statistical Society felt about government generally, and why there was so much of a push to have proper government statistics and proper censuses and so on, because whatever information we can get, however partial, is extremely important. And then there's a quote from the Daily Mail in 2014, which is that UK is home to 13,000 slaves, and the Home Office says the number is 4 times as many as previously thought. And that's based on work that I and Kevin Bales and others did at that time to try and get some handle on the size of the problem in this country. Why is prevalence estimation important? Well, the first thing is as an impetus for action. So to get the public to realize that this is actually serious. This isn't just a sort of very small problem. It's a big one, and it's one which may be bigger than that figure, but the point is that it's one which we do need an impetus for action so people can get the idea, and that politicians can. And the Modern Slavery Act, which was passed in 2015, it came into operation, came out of the strategy which that original research was part of. Second reason, to guide the allocation of resources. And I suppose there are two ways in doing that. One is specifically to say, we've got a problem of size X, therefore we need to put Y amount of resource into it. But the other is more generally just to say, this is important, you've got to put resource in. And I know from first hand that police forces and so on were really galvanized into action by the figures. However unreliable they may be, that were produced. And then the third, which is the most difficult, is to judge how well you're doing. And the reason that's more difficult is that you've got to actually tell the difference between now and next year. And I don't think we've got any methods of estimation that are reliable or accurate enough to do that in any short time at all. That's my personal opinion, but that's where we would like to work towards. And I would like to stress, for many or most of those objectives, you don't have to get a very accurate answer. Even an approximate figure is useful. Our current state of understanding is very, very partial. And I'd like to, again, with acknowledgement to my colleague Kevin Bales, say that if you think about climate change, 30 or 40 years ago, the work in that area was extremely approximate, and it wasn't understood. People had good reasons for believing that climate change was a problem. They tried to put numbers on it. And since then, there's been an enormous increase in understanding, and now we all have a much better idea. Even now, not such a good idea, but I think you should think of this as a topic where that kind of process is going on. And I want to stress, I do not claim that what I've done today or anything I've done in the past is panacea, but one of a number of approaches which between them will help build up a clearer picture. And I couldn't put it better than my old friend, the late George Box, who said that all models are wrong, but some are useful. And that is what I think about this. Okay, now, whatever method is used to find cases, there'll be many that aren't observed or detected. And criminologists use the standard term, the dark figure. That's a standard term in criminology, which means the figure that you didn't know about. And I might say that when the results of the work we did in 2014 were published, the minister at the time was briefed about it, and they said, oh, Bernard Silverman's done this work, and it's not based on it's not actually a count of a number of cases. And eventually she said, you know, I'm a mathematician, I can imagine the sort of thing that he did. And then she went on the radio and they said, how is it you used to think there were 2,477 cases, and now you think there are 13,000? And she said, those are the ones we knew about, and this is the ones we didn't know about. And then they went on to another question. So that's the dark figure, the ones that we don't know about. And there are many reasons why cases don't come to light. So Walsh and Hemmers, who are on Wikipedia, say that the gap in official statistics, the dark figure, is the largest for the less serious crimes. And that proves that most Wikipedia articles are wrong, but some aren't, and some aren't even always useful, because this is a very serious crime where the gap is very large. There are people from the ONS here who might tell us what they're doing in this area, but don't believe everything you read in Wikipedia, particularly that comment. It may be true for pickpocketing, it's also true for modern slavery. Here is a whole catalogue of reasons for underreporting, which I'm not going to read through, but there are several reasons. One is that you don't find the victims at all. The second is that even if you find them, they won't tell you what really happened to them. They might not even realize, and they may themselves be in some way on the wrong side of the law or the authorities, and therefore they may come from countries where you just don't trust the police at all, or whatever. And then coverage isn't complete. You can ask agencies to tell you what they know, they won't necessarily tell you. And finally, if you count prosecutions, they can be very difficult to achieve, and so again, that's another reason for underreporting. Now, a lot of my technical work today is on the matter of multiple systems estimation. I know there was a pre-meeting where people could learn about this, but the simplest form is what's called mark recapture or dual systems estimation. And it was purportedly proposed in 1895 to estimate the number of fish in a pond. And I've just set out the usual argument, but for the sake of people who don't know, the principle is this: you catch a number of fish, you mark them in some way, you release them, you then go fishing again, you see how many you catch the second time that you caught the first time, and you use that overlap to understand what the size of the total population is. So I might add, it's not that you make 3 observations, so you've got hundreds of observations here, and you observe for each one which catch they were in. And this approach is used in the census. There's a rather good little leaflet that we all got last time with the census, which explains it, written by Glenn Watson, I think, to estimate the undercount, because that's what we do in a census, which is another part of my world, to assess the overlap between the census and the coverage survey, and then you use those to get a handle on the undercount. And finally, 1895, there's a wonderful paper in the Royal Statistical Society journal called Who Gets the Marks for the Peterson Estimate? Peterson was the ecologist in 1895, and of course, according to Stigler's law of eponymy, or whatever it's called, the method was not invented by him, and it was not invented for that purpose, and he traces it back a lot. It's traced back a lot further, and originally it was always for human populations. So multiple systems estimation is the extension of mark recapture to multiple lists of data. So suppose we've got K lists, we'll call them 1 to K, and now this is where it gets a bit technical, I apologize. For each subset A of 1 to K, you can let NA be the number of cases which are observed in the lists in A, but no others. So for example, if your subset is 1 and 2, then N1, 2 is the number of cases which are on list 1 and on list 2, but not on any of the others. And the dark figure is the number that aren't on any lists at all, which for mathematicians is the empty set of lists, and that's N empty set. So that's just a bit of notation. And if K equals 6, for instance, there are 64 possible combinations of lists, and so each observation, of which there are thousands, can be considered to be a discrete variable with 63 possible values. So every case, every observation is in, you just look at all the lists it's in, and that gives you your 63 possible values for that datum. Here is the data that was used for the 2013 estimate. So in this case, there are 5 lists, and not all combinations of lists are shown. So for example, does that work? Yes. It only works when it's not on the screen. So I can't point on the screen because the pointer doesn't work. Okay, so for example, the column which says 695 at the bottom is the number of cases that are on the GO list only. And if you look along the column which has 76 cases at the bottom, that's on the overlap between PF and GO. I think that's correct, and so on. And finally, there's one case which is on 4 of the lists, LA, NG, PF, and GO. I'll tell you what these words stand for in a minute. And that means that there was one case there. Now, what this stands for are local authorities, NGOs, non-government organizations like charities, police forces, which includes the national crime agencies, government organizations, for example, the Border Force, and GP is yourselves, the general public. And so what happened was we had 2,000, at the time in 2013, there were 2,744 cases known about. The National Crime Agency had a register called the Strategic Assessment, and we went to them and said, what we'd like to do is to construct a table like this one. And they said, oh, there aren't any duplicates because we've removed them all. And I said, yes, I know you did that. That's because you want your total to be correct. I said, but we need to unremove the duplicates and find out where they came from, because they asked all these, and each one of these rows corresponds to a whole collection of agencies, of course, all the local authorities, all the police forces, all the NGOs are in touch with, and so on. And so they had to, what we had to do is, I had a colleague who spent a month in the National Crime Agency going through every single file and figuring out where each case had been reported and when it had been deduplicated and reconstructing that table. So that table was that table was extremely difficult to do, and we were not allowed to know any concomitant information beyond what's in the table, and I wasn't either. So that's all there is, that's all the data you have, and that's what you have to do. Now the dark figure is the last column, which has no x's in it because they're not on any list, and that's the one we want to estimate. A lot of work went into that table. Now, a little bit of mathematics. The model that I used and others have used as well is this. You assume that NA is the number of cases that are observed in the lists in A, but no others, and then you model the NA as being independent Poisson distributions, where it's a log linear model, where the log lambda A is written in that form, an intercept term mu, a sum of main effect terms alpha I, and a sum of two-factor interaction terms beta ij. Of course, you can have higher factor interactions, but with a data set of this size, I would have thought the evidence is likely pretty low. But actually, you can generalize all the work that I'm going to talk about to that. I haven't done that, but you can do that. The estimate of the dark figure is the exponential of mu hat, your estimate of mu, because there are no other terms in the model. And if you read what George Box says about parsimony, it's not actually very polite, but he's very strong about how it's important to try and choose a parsimonious model. And a parsimonious model in this case, of course, would mean you don't have all of the interactions in there. You try and find the important interactions only, and you fit those. And so if you want to do that, there's two ways around it. One is you choose, using some method, a particular subset of the possible interactions, setting others to 0, or you use some model averaging approach over all the possible, or many of the possible subsets. And I will explain why, in a way, what we're doing is a bit of a combination of both of those. Okay. So here's a few approaches that have been suggested in this context. This is not exhaustive, but here's some ideas. One idea is to fit terms stepwise, by analogy with stepwise regression. So you add your beta ij's in one at a time, and you choose the most significant using some stopping criterion. Now, in another bit of my own research world, I'm actually looking at that, and actually looking at how you can use a bootstrap approach to get a confidence interval which takes account of the model choice step. That's not today, because I wrote that after I wrote this paper, but that's coming. Another is to use an information criterion approach to choose between all possible models, and that's what's used in the standard package for this method called R-capture. And then there are two more Bayesian models. One's based on graphical models by Madigan and York, and one on Bayesian latent class models. I'm not going to describe those in detail, but I will refer to them a bit later. What's special about this context? Multiple systems, I don't know if Sheila Bird's here, she said she might be, but she's used the method to count intravenous drug users. And there are many examples of the use of this method to try and get a handle on hard-to-count populations. So even if you don't like the method in modern slavery, anything that does work on the method is useful for other contexts as well. And one of the famous examples, which I'll show you later, was to try and figure out how many people were killed in Kosovo in the 90s in a very short time during the Yugoslav war. Modern slavery data, however, is distinctive in that many of the possible observed list combinations have 0 counts on the data. So that even the 6-list version of the UK data, which is in your paper, has 0 counts for 37 of the possible 63 list combinations. And there's another example there where there are 255 possible combinations and only about 30 or 40 are actually observed, and the others are zeros in the data. And how do you deal with those zeros? That is important, and I'll mention it later. One aim of this paper is to explore the performance of various methods. And it's important, in my view, to explore their performance on actual modern slavery data sets, because it's only when we look at the real data that we're going to see the features that are important, and there aren't that many real data sets out there, and it's my hope that the discussion will get us to a point where we'll see more data put out into the public domain. So here are the data sets I'm going to consider. There's the UK data, which I've already shown you. There's data on victims of trafficking in the Netherlands over a number of years, which Peter van der Heijden, who's here, has actually worked on. There's data on victims in the greater New Orleans area, which is a paper by Kevin and Bales and me and Laura Murphy, which has recently come out. And then there's the Kosovo data of 99. And the first three yield sparse tables, as is absolutely typical for data in this area. And the fourth has non-zero counts in every possible cell, and you'll see the counts are much larger. And now a little bit about problems with sparse tables. So there's a paper by Feinberg and Rinaldo, 2012, which if you can read it between now and whenever and understand it, great. It is very, very technical and difficult. But in fact, when I worked on it, I found a mistake, and I wrote to them, I said, I think there's a mistake in the equation such and such, and they said, no one's ever pointed that out. And I said, yeah, well, yeah, okay. Anyway, so Chan, Vincent, and I have done some work on how all that relates to multiple systems estimation. So that's not for today, but I'll just tell you that you can get non-identifiability, but that can only happen if all the two-list interactions in the model, and even then under special conditions. So non-identifiability isn't usually a problem, but you can get non-existence of the maximum likelihood estimate, and that's a bigger issue. And they point out that it is not accounted for in GLM, which is the standard generalized linear model program that everybody uses. It does not incorporate a check of this problem. And now, in my other paper, there's an efficient algorithm that actually can check that estimates exist for all of the possible model choices for a data set. And you need to know how many possible model choices there are, because if you have, say, six lists, then you have 15 interactions, and so there are 2 to the power of 15 possible models. It's an enormous number, but there's an algorithm which actually can make it a bit quicker. I've worked on that. And if you use the BIC approach, which I'll show you, many of the models considered throw up, I've just mentioned your work, but you're too late. Hi, thanks for coming. Many models consider the BIC approach generate warnings. So the BIC approach I'll describe in a minute, you get warnings all over the place, and I don't think if you get warnings from a program, you should simply ignore them. I think you've got to understand why they're there and do something about them, which is one of the things that we do. And finally, about information criteria, the BIC depends on use of information criteria, but that depends on conditions which actually in the sparse table case don't necessarily hold. So, because in order to do information criteria, technically speaking, you have to do a quadratic expansion of the maximum likelihood estimate around the maximum, and if the maximum likelihood estimate is at minus infinity or something like that, or way off into the distance, there isn't a quadratic expansion. You can't do it. So the theoretical justification for information criteria just isn't there. Anyway, right. So there are not too many technical slides in my presentation, but this is what we actually do. So this is a Bayesian approach to parsimony. Ideally, you'd like to use a prior for each beta ij, which is a mixture of an atom of probability at 0 and a normal distribution. So in other words, you're saying maybe the parameter's there, maybe it isn't, and so we'll use a Bayesian, we'll put a prior on that. The trouble is, well, that required a lot of, I haven't done that, but in work I did with Ian Johnston some years ago, we showed in another context that you can approximate that by using a thresholding approach, where you first of all do an analysis with the parameter in, all the parameters in, and then if their posterior mean is too big relative to the to the standard deviation, then you keep it, and if it's small, you say, if I'd used the real Bayesian approach, it would have essentially been estimated as being in the atom of probability at 0. And the choice of threshold corresponds to the prior probability. Now, that I did because existing software allowed me to, and I didn't have the time or the resource to actually implement the full Markov Monte Carlo or something approach to doing that, but actually Ian Dryden has done a bit of work actually implementing the real thing. But so what you're seeing is an approximation to a Bayesian approach, which says, let's suppose that we need a lot of convincing for a parameter to be in the model, so we'll give it a big prior of being 0, and then if it's not 0, we'll give it a normal prior. Okay, so here are some examples. Now, what I'm going to do is to go through some real data and see how all the existing approaches work. So the first thing is the stepwise approach, and this is the data the UK data, and what you can see is that that different methods don't give very different answers. So roughly speaking, the italicized figure is the one which gave the famous 10 to 13,000 approach. This is where you choose the model by a stepwise approach, adding using maybe a not very reliable criterion and stopping when you start getting effects that are not significant. So that's that. If I were to do this again, I would use a bootstrap method which took account of the model choice that I will report in subsequent work. If you use the stepwise approach on the real data sets, you get something rather alarming. So the Netherlands data, for example, you can see that the stepwise approach gives a completely different answer if you put the two smallest lists together, which is not actually a very good idea. You would like to feel that because in a sense what you put in it, how you coalesce your list is a little arbitrary. So unlike with the UK data where coalescing the lists didn't matter, in the Netherlands case it matters a lot, and you can see you get a completely different answer. And also in the New Orleans case, so it should be said that to use 8 lists for New Orleans is a lot of lists. They're very small, some of them, but that's what you get. And the Kosovo data, you get the figures down the bottom. Now we move to the BIC, which really started worrying me. So this is where we take the UK data, and this is the default. This is just using the R capture program. So what you do is you fit every possible models, and because a 6 list would lead 32,000 models, I didn't do that. You use a 5 list data, which only does about 1,024 models. And so there's 1,024 points. And the way it works is it calculates every possible result, and it chooses the one with the lowest Bayesian information criterion. And if you take the graph on the left, it chooses, that's the default choice, default plot, it chooses a model, very similar result to the one we got from the stepwise method. But if you then do omit outliers equals false, you get the one on the right, which shows that the very best model under the BIC corresponds to something out in that cloud out there. So that's an instability in the BIC method. And I might also say that lots and lots and lots of those points generate a warning. So when you run the program, you get literally hundreds of warnings, and you can't, in my view, simply ignore them. But there you are. Now, if we move to the Netherlands data, you get this, where this time the maximum is about 50,000, which is similar to the method you got from 6 list data. And then there's this kind of comet's tail of points out there, which actually is obviously what was being picked up in some way by the other method. So again, it's not unstable as such, but you can see there is something odd going on, which we don't understand. We need to understand. And now we'll move to the method of Madigan and York. And this is for the UK data. So Madigan and York really think their biggest mode is the right-hand one, which is the big number for the UK data, and so again you get a bimodal result. Slightly strange. And then the Netherlands data. Well, the Netherlands data, Madigan and York, looks great. That's what the standard approach gives. And then when you actually say, aha, well, let's suppose we could have as many as 250,000 victims, which might be unrealistic, then you begin to see the upper component as well. So that's something that happens. Okay. And then finally, we'll move to the Dirichlet process mixture approach. And for the UK data, this ignores, the numbers are in front of you if you want to look at the paper. This ignores the lower component found by the Madigan and York method, so it gives you the higher thing, except when you have only 4 lists. And for the Netherlands data, it gives the big number or the small number, but the other way round from the stepwise method. So the 6-list data give you the big number, and the 5-list data give you the small number. I will say that some of these methods you can use for any number of lists and others you can't. So in particular, you can't use the big method and you absolutely can't use the Madigan and York method for more than 5 lists. Okay, bit of a tour through, but let's now finally look at the results for the Bayes threshold method. And this gives, in my view, stable results. And these are the quantiles of the posterior when you use variance 1 and threshold 2, which is the variance 1 is the variance parameter of the Bayesian prior, and the threshold corresponds to the choice of the size of the atom of probability, the amount you have to be convinced to take yourself or to get the point into the model. So the 2-step nature is only an approximation to the actual Bayesian method, and it's an approximation which has been used in other contexts. So to summarize about the Bayesian threshold model, I think it shows reasonable stability for all the data sets. For example, when you leave out or combine lists, because one of the ways of checking whether what you've done makes sense is to say, well, let's suppose I had combined this in a different way, what would I get? Or let's suppose that I didn't have that particular list. So if I go right back to the, so in particular, and this is something I've talked about elsewhere, where are we? Sorry about this. There, that's right. The GP list, that's the general public. Those are cases known by the general public. Now, the trouble is, the general public do things like ring up and say, you know, I don't like the look of what's going on in that car wash down the road. But there's a victim there. And they might not give enough information that you'd be able to correlate that victim with another list. The other agencies collect enough information to make it reasonably reliable to do your collation, but the general public not necessarily. So one of the things that I did when we did the analysis was to say, okay, let's regard the GP list as unreliable, let's leave it out, and you get the same sort of result. So occasionally you'll want to find robustness for that purpose. And the other thing is, if your lists are very small, it's not unreasonable and it's standard practice to combine them to make larger lists. And again, you can do that, and you would like things to be stable. Now, the Bayesian method works well both on the New Orleans list, which is very sparse, and on the Kosovo data list, which is much less, not sparse at all. It seems to automatically rule out what I think are implausible secondary estimates in the data. And it also adapts well between data where there are strong interlist effects, for example, Netherlands and Kosovo, and where the effects are weak, for example, New Orleans. You would say, if you only knew more, in the New Orleans case, we weren't even allowed to know what the agencies are. So the New Orleans case, the only way they would give us the data was to anonymize it to the point that we were not even allowed to know who is A, B, C, D, and so on. You might say, well, how can you work that way? You have to, that's all you've got, and that's how sensitive data can be in this case. The results are relatively insensitive to the choice of threshold, provided you use a threshold at all, and the choice of prior variance. And that seems to be because in most cases, either the interaction is quite strong, or it doesn't give you enough evidence that you really want to include it. And the tentative standard choice is variance 1 and threshold 2. And for the sake of, you'll see in front of you that with this choice, the Netherlands estimate is slightly higher. Perhaps that's a nod to the upper mode. So, in conclusion, in this context, you can't design the surveys or captures in the way you would in a census or an ecology context. So in the census, and I've got colleagues here who, if they feel like it, will tell you more, you can, well, your first survey, of course, is purportedly everybody. It isn't quite. And your second, subject to the taxpayers' money, you can make your second survey as large as you like. But in this case, we can't do that. We have to make use of the data that we have. So it's not like catching fish in a pond where I could carry on fishing all night. I've only got to work on the data that I'm given. So that's a different context from many of the things. Sparse data are the norm, not the exception. So we have to worry about sparse data. The Bayesian method, I might add, automatically deals with sparse data because it uses proper priors. And if you use proper priors, then all these problems of identifiability and non-existence, I won't say go away, but they're not problems anymore because the estimate will work its way out from the prior. Proper prior, you'll get a proper posterior. You won't have a problem with that. In other work I've done, I talk about what you do if you're not using a Bayesian method. We absolutely need more data in the public domain to develop methodology. One of the other problems is, unlike other contexts, there is no right answer, there is no ground truth. You will never know how well you're actually doing. And therefore, all you can hope to do is to get methods that are reasonably stable and work well as far as you can tell on the data you actually have. And it's true, it would be great if all data were put out publicly, but there are very genuine privacy and confidentiality concerns. Because if people come forward, they obviously have to be given assurances of confidentiality, because we're not talking about fish here, we're talking about human lives, and human lives in a very, very delicate and difficult situation. And so what we need to do is to find ways to encourage putting data out into public domain, but obviously keeping in mind privacy and confidentiality. And we absolutely need to integrate multiple systems estimation with a wider range of approaches. So it is just one approach. All models are wrong, some models are useful, and that we do that in order to understand the modern slavery issue in depth. And I've got 2 minutes. I promised I would finish exactly on time. And so let me just give, these are just a few questions. Can the method be developed to handle concomitant information? Sorry, I mean, can the Bayesian method I've described be developed? Obviously, the answer is yes, but it would be interesting to do that. What's the best way to discern whether the overall prevalence varies over time or between sectors or geographical areas? Again, I think we need real data to try and work on that. Can the approach be extended to fuzzy matching between this, where you say, I think this case is the same one, not quite sure? And are there particular patterns in data in this area, and can these contribute to a deeper understanding of the problem itself? I don't mean a deeper understanding of multiple systems estimation, helpful that would be, but a deeper understanding of modern slavery. I hope that today's discussion will encompass broader issues to make it a real resource beyond the paper itself. I didn't, if I may say, originally intend this paper discussion. It's great there's so many people here. But actually, to have the chance for the Royal Statistical Society to use this as an opportunity to discuss the wider issues around the quantification of this awful crime, if that means that one fewer person is victimized, then what we do today will have been worthwhile. Thank you very much indeed. Thank you.
Okay, thank you very much for the invitation to propose the vote of thanks. So it's a great honor for me to do that. Let me see. So, oh, here. Sorry, thank you. So, it's really a great paper, a magnificent paper. So it has 7 sections, and I must say that every section is interesting in itself. So starting with the introduction, as Bernard was saying, the problem is important, and we should always see that. And it falls into actually one of the benefits of this paper is that it brings out this problem of hard-to-count populations, so at the example of modern slavery, but many other problems do occur, such as family violence, firearm possession, and things like that. And when I was preparing actually my comments for this proposing the vote of thanks, I read the German leading newspaper and found an article about a certain problem in poverty in old age. We have a situation in Germany where certain people have to take private insurance while, for example, they are self-employed. And then these private insurance have the property that they become more expensive with increasing age. And when they get in the pension age, they are so expensive that they cannot afford it. They cannot buy it anymore. And they fall out of the system. And now here comes in the sensitivity. It's a law in Germany that you have to have private insurance. So they do something illegal. And the article said, well, it's estimated, it's somewhere between 30,000 and 500,000. Nobody knows. Nobody really knows that number. Yeah? Interesting. So it's just like, had nothing to do with slavery, but it's a type of problem where it's a hard to reach population. So I find this introduction in itself very important and interesting, and actually also the data sets. Everything starts with data. And one of the problems is in capture-recapture is that we need as much information as possible. Yeah? The more information we have in terms of, for example, coverts. Peter van der Heijden pointed that out in his tutorial, then we are better off in the situation. But this is very difficult as these areas are very sensitive. And for example, the third data set from New Orleans, it is very, very vague actually in the paper said what this is really about, what kind of like problems with law enforcement service providers is. So, and yeah, I was thinking of what could that be, yes? And so you probably know more than you actually could write. And then we have, of course, the well-known data set and the Kosovo conflict. So all starts with data and the quality of the data. And the more information we have, the better it would be. So, and then actually the situation, I don't want to repeat this, is that we are dealing with a multiple table, and we have when we have k lists, we have 2 to the power of k entries, and observed frequencies are 2 to the power of k minus 1. So that's the one cell we are interested in, and we want to do estimation. And then I find the following quote very interesting. Yeah, overall, the results for the 5 list data demonstrate that the estimate of the total population can vary considerably depending on the model that is chosen. That is a basic message, and I think that comes out wonderfully. We just saw these displays, and this is, I think, I can promise you that this display will be, used again and again. It's a very, very useful display to see really what is going on, because ideally, we want to have a funnel really, which becomes very narrow on the top. At the top we are with the best fitting model, and but it's not the case. So it's all over the place. So we have here, this is actually the situation with outliers included, where we actually have a number of models with similar fit, and the point is really that we have not the same population size. The population size is varying, and that's actually more pronounced here in this data set from the Netherlands, where you have these actually at the top, where everything should be narrow, or we wish it would be narrow, is not the case. So I find these graphs very, very useful and helpful, understanding the problem that I think were in the literature pointed out before, but I think not worked out in such a clarity. So that was particularly, I thought, very delightful to see. Then we come to the Bayesian approaches that have been used before. The graphical models method of Madigan and York that uses every decomposable graph model of dependency between the various lists, and then we obtain the joint posterior for the models and the total population size. And I think we have seen this picture. And what I think what is, from my point of view, the bottom picture is fine. I can interpret that, but I have a problem with the top graph, because it looks like a two-component mixture. And how would I interpret that? So that's really the difficulty here from my perspective, and that's kind of like nicely worked out. Then the second classical method is, in the Bayesian sense, is the Dirichlet process mixture, which is also briefly mentioned. And I think the comment that is also taken here from the paper summarizes it nicely. Unfortunately, neither method escapes the instability that have already been seen in the actual data set. So then we come to the Bayesian threshold approach, which is suggested in novelty. So we assume here certain priors for the intercept main effects, uniform priors on the real line, and then interaction parameters receive Gaussian priors with a variance 1 over lambda. And then we have this this thresholding approach, so that interactions that are falling below this threshold are set to 0, and then this whole thing is done again. That's in essence my understanding of how this works, and I think that we have seen that table here, so we see this in the median of the posterior distribution, this nice, relatively nice stability of the estimates over the various thresholds that are possible and variances, and seems to be quite independent of what is done there. So that's the first impression. However, I actually would have liked if I would have been a reviewer, but I'm not. So, but if I would have been a reviewer, I would have liked to see the posterior distribution if it avoids this kind of mixtures that we have seen before. So that is actually, we don't see that from here. I assume it does not, but it would have been nice to see. And then, of course, a choice of the parameters, the tuning parameters, the threshold is probably would be useful to see some more on this. More general, I thought, why not include in this new suggested method, 2 minutes left, I'm done, why not include higher order interactions? If this method worked, it would also kind of kick them out. The method, if I understand it correctly, works only with main effects and two-way interactions. So, of course, the number of models explodes. So that is my question to this. And as the last point, I thought this idea of internal validation that was put forward in this paper that you mentioned in your tutorial from the working group on capture-recapture. There are two important publications in the American Journal of Epidemiology 1995, where this was suggested. So basically you are fitting the models for a conditional table where you have this empty cell filled, and then you can actually see how well your models are doing. So that I thought was a very nice idea, and is, from my perspective, too not enough used. So I'm coming to the end, and it's my great pleasure, having read this magnificent paper, it gives me a great pleasure to propose a vote of thanks here. Thank you.
Thank you. And it is a great pleasure to second the vote of thanks for this paper, although you might wonder, why me? I'm a clinical trials statistician, retired. But a couple of years ago, seeking to widen my academic horizons, I enrolled onto an MA course on international slavery studies at the University of Liverpool. And there, during the first term in a module on modern slavery, I first came across the problem of estimating the number of victims of such exploitation and the paper of Bales, Hesketh and Silverman, which introduced the MSc approach of which we've heard tonight. It appeared to be a welcome bridge between the linear modelling world of my former discipline and the problems inherent in my new one, as well as a possible free pass for my essay. In fitting the model defined by equation 1 of his paper, Professor Silverman makes two assumptions. One, that two list interaction terms may sometimes be zero, and two, that three list interaction terms are always zero. To include a two-list interaction, he requires evidence of its significance via forward selection, even though the power to detect interactions is low, and it's absolutely zero if the lists do not overlap. For me, this two-stage analysis was reminiscent of an old controversy in my world of crossover trials, where patients are randomized between group 1 and group 2, group 1 receiving treatment A in period 1 and then being assessed, treatment B in period 2 and then being assessed. And this is how I used to teach the analysis. First, test for carryover. That is, can the period 1 treatment affect the period 2 assessment? If it's non-significant, no carryover, analyze both periods. If it's significant, throw away period 2, analyze period 1 only. And I did that happily until Peter Freeman wrote a paper demonstrating that such a two-stage procedure inflates type 1 error and can reduce coverage of 95% confidence intervals down to 56%. And after that, two-stage procedures were neither taught nor used, as far as I was aware. So, with colleagues from Lancaster and Liverpool, we investigated this problem further using the 5-list UK modern slavery data that has been discussed tonight. And the first fit that we did was just reproducing the forward selection method that you've seen in the table 5 tonight, with an estimate total number of modern slaves of 11.3 thousand, and a 95% confidence interval of 9.9 to 13.1. My natural reaction is just to include all two-list interactions regardless, and that gives a similar estimate, but the confidence interval is considerably wider. Then, using that latter model, we simulated 10,000 replicate data sets. The true Poisson mean was, of the dark figure, was 8.4 thousand. In the 10,000 forward selection analyses, the average estimate of the dark figure was 12.2 thousand, and the coverage of the 95% confidence interval was only 39.1%. If we analysed each of the replicates with all two-list interactions, then the analysis was much more satisfactory. And tonight we have heard of potential investigation into bootstrapping to solve such a problem, and that sounds like a good idea. But assumption 2 is that three-list interactions are always zero. Tonight's paper has not explained why this should be so, although it has been acknowledged in the oral version. Is it possible to explain to investigators who are unfamiliar with log linear modeling what this assumption means? Because I have been unable to do so, particularly discussing with my lecturer at Liverpool. From a fitted model with all two-way and three-way interactions, 10,000 replicate data sets were generated and analysed. The true Poisson mean for the dark figure was 0.6, 645. So an alternative explanation is that there are three-way interactions and there are fewer modern slaves. The forward selection was applied to all 10,000 data sets. The average estimate was 12.8, and none of the confidence intervals included 0.6. All two-list interactions was hardly better. And simulations of models incorporating the three-list interactions were totally unsatisfactory. So, do Bayesian approaches solve such problems? The Bayesian threshold model of section 6 uses priors that incorporate assumptions 1 and 2. And from my understanding, a prior should reflect investigators' beliefs. Do investigators even understand what these priors imply? If they don't believe in the prior, then the posterior is irrelevant to them. So, my conclusions. I think that the MSc approach is unreliable, and I really do wonder whether it's futile to seek the dark figure. What we really want to know is changes in population of victims over time and differences between place that can be tracked using the number of observed individuals. It has great shortcomings, but they are transparent to everybody who reads the report. Nevertheless, it gives me great pleasure to second the vote of thanks for discussing and getting into the RSS this very important problem and the need to find solutions. So, thank you.
Ian Diamond, National Statistician. Can I start by thanking Bernard very much for the paper? And one of the reasons that I'm incredibly keen on it is that I think it is incredibly important that we use the most sophisticated techniques possible to inform government in every level. And I think the influence that this work has already had in raising the profile, as has Bernard said, of this appalling crime is, I think, notable. And so the first point I would make is that I think it is really important that we continue to seek to do work like this as much as possible and to publicize it as much as possible, and also to challenge it at such as the Royal Statistical Society. I think is incredibly important. I was also incredibly pleased this paper to see the work build on Richard Cormack's work, and I would note that in another paper not referred to, Richard, I think, developed some of this work on some issues in Glasgow around people who were extremely disadvantaged, and I think that work took forward the profile likelihood in a very helpful way. You talk about the GP list, and you also, in your oral work, Bernard, talked about the potential with censuses. And the point that I would make firstly is that while it is true that when one does a census, one hopes, a population, however, in some of those areas which are under-enumerated, one is dealing with fairly sparse populations, but if one is serious about getting resources to what are often some of the most disadvantaged members of society, then it is incredibly important that we work very hard to identify and to use all techniques that are possible. And I do think that in trying to get estimates of those people who are homeless at the time of the census, this approach has an enormous benefit. However, if I just may say a word about the GP list and a word about censuses, we rather tend to believe with administrative data that these data are absolutely accurate in every way. Actually, they're all subject to error, and censuses, we know, suffer not only from under-enumeration but from over-enumeration, and GP lists are known to have a degree of overcount in them. That means that we could be, and some of the work that we have tried with ONS has shown that you can start to get very big overestimates when you have over-enumeration. So my point is very much that some of the GP stuff could reflect some of that over-enumeration, and that we need to have a view, I think, not only of the lists, but of the accuracy of the lists. And I don't, sadly, have an algorithm that tells me how to weight the lists, but I do think we need to think about the accuracy and the potential accuracy of lists when we are putting them together. That said, I think there is an enormous amount of positive things to say about this paper, and I urge everyone who hasn't yet read it to read it carefully and to seek ways that we can use these techniques to address some of these incredibly important questions. Thank you.
Thank you. Professor Silverman highlights smallest list sizes and combinations thereof, the need to identify and deal with empty or unobserved overlaps between analysed lists, which may relate to three-way interactions, prior belief in there being few interactions, and hence choice of prior variance, and the setting of a threshold for credible interactions, 2 or 5. In the paper, I might have added 3. A neat byproduct, I think, of thresholding, provided it stays the course of bootstrapping, is that it seems deftly to deal with one of the main drawbacks of MSc estimation, namely the wide, unwieldily wide posterior confidence intervals, which make them weakly informative, including when you want to compare changes over time. So, attractive as these features are, Bernard, I would like to mention some practical reservations, which I think is what Bernard was calling for in his final remarks. First, even readily identifiable covariates, which may determine list propensities, are sadly absent from most data sets on modern slavery. I think of gender, adult, child, and the type of victimization, be it domestic or sex work or outdoor labor. Secondly, clusters of victims may be rescued together, notably because of information given to the police by a prior escapee. And so multi-systems estimation needs to evolve methods to deal with this type of clustering and also affiliated networks where you've got the same person controlling enslaved individuals in different locations. Thirdly, list combination should consider other list attributes than size alone. For example, some non-governmental organizations are set up to deal specifically with the problems encountered by female or child victims. Fourth, a different type of threshold matters when assessing UK's extent of modern slavery. Potential victims who pass the UK's initial reasonable grounds test may not receive a positive, conclusive decision. Indeed, approximately 55% only of UK's potential victims receive a positive decision, and that eventually after considerable delay. So fifth, Professor Silverman has alluded to the difficulty of matching across lists. Sensitive consideration could be given in consultation with victims to whether there is a role for DNA sampling, for example, in reuniting trafficked victims from the same family, and as we have sadly learned just in the last few weeks, even the identification of those victims themselves. Finally, a public health approach to caring for and follow-up of rescued victims should address theirs and others' morbidity and mortality in the longer term, or at least in the short term, so that one might compare mortalities, for instance, en route to the United Kingdom during victimization and for at least 2 years after rescue or escape, so that we learn better how to care. Thank you.
I too enjoyed this paper very much, but I want to make a couple of points. And one is to start with this wonderful diagram which intrigued me, so I thought I would go and look to see what those models are, which are the ones which have the high likelihoods, so the ones that appear under the thick black curve but with the dotted lines. So I used Bernard's nicely provided data and software and went off and had a look at those. So I took the 5 models that have the highest likelihoods, the highest peaks in their likelihoods, and I found 4 of those were in the lower peak, and those are on the left-hand side of my table. And 1, 2, 5 means that I think there's a 3-way interaction and all the 2 ways inside. So this is me deconstructing the software to try and work out what the models look like. So I think there are 3-way interactions in these, although there are 2-way interactions in other bits of the paper. So I got those 4 models on the left-hand side with their maxima of the likelihoods, and this one model in the upper mode on the right-hand side. And what I was interested in was whether I could see something which would tell me what was causing the model to end up in the upper mode. Number 5 in my my representation here is this general public data set. And my interpretation here is that there are quite a lot of interactions on the left-hand side, in the left-hand column, which involve this general public data set. So that's telling me that the main effect is getting modified a lot in this log linear model. Whereas on the right-hand side, there's only this one interaction which is doing the modifying. So I'm relying a lot on the main effect for the general public list. So I think that's consistent with what Bernard was telling us, that says that the general public list is a bit different to the other ones in this particular case. And that leads me to wonder whether I can say something by using a process like this one about how consistent or coherent the lists are among themselves, and whether you could say something which said that list 5 here doesn't look coherent with all the other bits of information I've got. Is that telling me something important about the quality of the lists? And then I want to go on a little bit to a more general thought about data sources and quality and linking. It's a point that actually that's already been made a couple of times already, but I'm going to make it again. So the data sources are naturally imperfect for this sort of data because modern slavery is really difficult to observe and really difficult to measure, and even the concept of it is difficult in some cases, as we just had. So the data is going to be uncertain. And the paper deals a lot and very carefully with model uncertainty, but it hasn't really talked about data uncertainty. So in the multiple system estimation, the quality of the linking is going to be really important. So those cases which do appear on more than one list, you'd like to identify those and link them perfectly. Whereas cases that are not linked, you'd hope to be a perfect situation where they're actually different people. You didn't miss a link. And if the linkage is not perfect, then we will affect possibly quite substantially the estimates we get. And Bernard already suggested fuzzy matching as a way to look at that in the future. But I think there might be some other things that we could do as well. So we could look at the sensitivity to linkage errors. So one way to do that might be to adjust the data. If those of you here this afternoon for Peter van der Heiden's presentation, he showed what happens when you have one extra link that shouldn't be right, and also if you take just one link off. We could try to do the same thing. It's not so easy when you have multiple data sets, because it's not so obvious which bits you're going to adjust in the data. But I think it would be interesting to do a sensitivity analysis where you do make those adjustments and then try to refit the models and see whether the sorts of outcomes you get are stable. So I could go a little bit further, and if I got from my first thoughts about which models are which based on the interactions, if I could get some sort of idea about how far away a data set is from consistency, then maybe that's the data set that I want to adjust most. With this paper, we've very helpfully got the data sets which people can now start to use, but I would really like to have some linkage metadata to go with those. You described how that's really hard, even in the American case, even to know what the data themselves are, but it would be fantastic if it was possible to have some information about how the linkage has worked, so that we could have some evidence. And in fact, there is some recent work on extending multiple system estimation to deal with linkage error. So in summary, I found this a fascinating paper, not least because it shows how the estimation can be slightly odd. Thank you very much.
Hello, I'm Sarah Henry. I'm also from the ONS. Thank you. I too want to thank Bernard for this incredibly important work. It's important methodologically as well because, as Ian Diamond said, our heads are now buzzing with the other applications that we can use, especially with the census and other unrepresented communities. My questions, I think, relate a little bit to the data itself. First of all, what more do we know in the data that could be useful to us? For example, is there anything in it about the sectors? Your first slide referred to examples of sectors where we find modern slavery and trafficking. I wonder if the data includes that information as well. The sectors are actually incredibly important here. I maybe should have applied the methods as well to try and estimate the size of these sectors, but I didn't. I just Googled, and I started off by Googling how many nail bars there are in the UK, and I also Googled to see how many car washes there were, and both those sectors are quite big. So nail bars, the figures that I found were from 2011, so it's quite old data, and it estimated that there were about 2,000 nail bars. My gut feeling is that that's a bit low, and something like 20,000 car washes. If you add in all the sectors, the size of the sectors, then it feels like the estimate for modern slaves is a bit low. So I'm wondering if we can look at the data and also see if we can have some independent analysis about the sectors themselves and see if we can conclude anything about that. The second thing I'm interested in the data is the year in which the data is collected. I think the term in the paper that was used, that was people who were trafficked, was in one of the tables. Was that trafficked in 2013? I might have read that incorrectly, but I think that once you're trafficked and you stay in a country for a while, then you're a modern slave for probably, unfortunately, a very long time. So I'd be interested in that as well. But thank you very much again for both the methods and the subject matter.
Good evening, I'm Jess Sparks. I'm from the University of Nottingham's Rights Lab. I lead the Anti-Slavery Ecosystem Project, and I specifically work on measuring modern slavery in the fishing sector. So just to highlight a different approach to MSc, building off Bernard's work, is that I'm actually getting ready to launch a project where we use oral histories to reconstruct list of cases. And the reason why we're using oral histories is because it goes back to this issue of linking, so we have better control over the cases and the collection of data. And the reason why I've decided to use multiple systems estimation is because after working in the fishing sector for over 6 years, I can tell you that fishers are not observable. They don't come onto land, they stay out at sea. There's no way to calculate estimations off of observations. In fact, they are hardly seen in the national referral mechanism, and when you talk to dock workers and dock authorities in particular, they're saying that the estimations are much higher, but we don't have access to these individuals because they're not allowed on land, and if they're not on land, they're not seen and they're not measured. Thank you.
Okay, so I'm Martin Ridout from the University of Kent. Like other people, I've really enjoyed reading the paper and the presentation tonight. I just wanted to make a small and specific thought. So there's been an emphasis in the paper on focusing on the real data. And then, of course, there's the difficulty that you don't know the true answer. And so we've had the suggestion of looking at consistency when, for example, lists are combined or a list is omitted. I wondered whether it was also useful for assessing the methodology to condition on a list and just analyze the people who belong to a particular list, so that then your dark number estimate is an estimate of the number of people who belong just to that list, and so it is accessible in the data. It doesn't actually necessarily help you much with the answer of how many modern slaves there are, but it makes a contribution perhaps to seeing how robust the methodology is. Thank you.
It's another very small point. Kevin Bales. I'm the research director of the Rights Lab at the University of Nottingham and co-author with Bernard on the 2015 paper. I've been working in the field of modern slavery for quite a long time, and measuring prevalence has been extremely difficult, especially beginning in the late 1990s when no one seemed to even believe that there was such a thing. It was very exciting when we began to have some rich benefactors who supported us in commissioning Gallup world polls in a number of developing world countries. So we could do random sample surveys. We soon discovered that you might be able to get a reasonable estimate from a random sample survey in some developing countries, which were not questions being asked of, are you in slavery? But in fact, household questionnaires, which said, has anything like this ever happened to anyone in your family? And you would have these secondhand reports, but you would be able to extrapolate and estimate from those. But we discovered, of course, that any attempt to do random sample surveys in rich countries and developed countries were not possible. The total number, the prevalence just seems to be so low in well-off countries that in a sense They are minnows, and the net that you're dragging through as a survey through the population is just too wide to catch those minnows. That put us on a search for another method that we might use. And that led us to multiple systems estimation, particularly from the Human Rights Data Analysis Group and the amazing work that they had done on mass atrocities in places like Bosnia, but also Peru. Now, when I first spoke to people at the Human Rights Data Analysis Group, there was an interesting tension in that group, because some said, this only works on dead people, and other people said, oh, it might work on live people. And I said, well, if it works on fish, it ought to work on live people, but that's a different kind of controversy there. I thought that would be more like a joke, too, but it didn't. I've never worked as a room full of statisticians, and I now understand how tough that can be. So when Bernard was able to help us to bring this to fruition, we understood it for the pioneering attempt that it was, and we're very excited to be able to bring that forward. I was amazed at the rapid uptake by the then Home Secretary, and then into the government and into the legislation, and that was fantastic. But in some ways, I almost think that was premature, because it's a technique which is just tonight, several years later, reaching points of refinement that I think are very important. I want to make one other tiny point, and that's about the dark figure, and the dark figure of this crime in particular. That estimation of the dark figure normally comes from crime surveys, and of course the British Crime Survey, as it was, helped us to allow and calculate what dark figures might be for specific crimes. But slavery crime is uniquely different in that most crimes are treated as an event, a crime event, which can be counted at a particular point in time. And in fact, most crimes that occur last somewhere between 30 seconds and about 10 minutes. However, this is both legally in its definition in international law and in other ways defined as a crime of indeterminate duration. In other words, when the slavery crime begins, no one knows when it will end, and it can last from minutes to decades or to the entire length of the life of the person who's being victimized. That removes it from a lot of the use that we would normally use for dark figures. And it also makes that understanding of dark figure much more important when we can bring a technique like MSC to bear. That's all. Thanks so much.
So Thomas Lewis from Bloomberg School of Public Health in Baltimore has sent in the following one, and the following points merit consideration. So the log linear model on page 7 is the standard main effects plus interaction format. It's broadly applicable with Feinberg 1972 an early example. However, when combining evidence from more than 2 lists, a logic parameterization is worth considering. For the logic model, to set j equals 0, 1 up to n for the index potential victims and consider 5 lists. With AJI equals 1 or 0 according to whether a potential victim is or is not on list I, and then let AJ equal AJ1 up to AJ5. There are 2 to the k candidate indicator regressors, I of AJ, and the dark figure is A0, which is 0, 0, 0, 0, 0 in this case, 5 lists. It's possible that omitting some of the A vectors with 2 1s and through the prevalence of though the prevalence of a 3 list appearance is low, including a few with 3 1s, all with thresholding or shrinkage, will increase stability and improve performance relative to the standard parameterization. And it talks about thresholding. Thresholding stabilizes and is attractive when simple structure is the primary goal. However, stabilization by standard shrinkage is likely more effective when making predictions. For example, the value of lambda, the empty set, or the slope on A0. Related, the use of a slice slab prior is an alternative to Silverman's Z-score thresholding. Fuzzy matching is worth considering, with Steele et al. Reporting on matching administrative records. Sorry, oh yes, indeed, thank you. Do yell at me, I'm reading it on a piece of paper as well, so I don't get to scroll the paper. Now I've gone too far, haven't I? with you? Okay.
I'm used to using
Thank you, sir.
I'm used to using, yeah, hang on, where's the thing gone? Mouse has disappeared off the other one. Want to go back. This is just, yeah.
Previous page, I'm sure it'll be on somewhere. Fuzzy matching is worth considering, with Stewart's et al. Reporting on matching administrative records. As shown by Louis et al. In the genomics context, there are considerable benefits to retaining the fuzziness, in other words, operating with fractions, rather than selecting the highest probability for a probability match. And survey application, in well-curated multiple system contexts, such as post-enumeration surveys, there are challenges, but they're of an order of magnitude less than in Silverman's application. Ian Diamond already mentioned those. It's pleasing for design that Sir Bernard closes by discussing designs with the potential to improve performance, including covariates or use of an informative prior distribution may produce identifiability and preserve validity. Number 2. Yes, Kyle Vincent, an independent researcher.
That's the whole, yeah.
This paper draws the academic community's attention to the need for more rigorous estimation procedures when studying populations comprised of modern slavery victims. Silverman's use and comparison of frequentist and Bayes approaches highlights the benefit of exploring both approaches when inferring on hidden populations based on administrative lists. Mark recapture methods are currently being adopted and tailored for multiple systems estimation. Within the context of multiple systems estimation, applications for studying hidden populations, there are likely to be more prevalent or new challenges that will be manifest. For example, since there is a need to preserve the confidentiality of individuals captured on administrative lists for MSE, sharing of detailed information across administrative sources is likely to be limited. Hence, it could very well be the case that missing or erroneously entered information exists for linking individuals across lists and or records of their covariate information. I'm hoping that the author can make a few comments regarding these challenges, in particular where future work on these topics should be directed. A Bayesian framework can facilitate goodness of fit approaches to assist with choosing a model and its quality of fit based on the posterior predictive distributions. For this reason, does the author have any thoughts on using the posterior predictive distribution to aid in choosing the most suitable thresholding parameters? If so, how does the unknown population size affect this approach? Finally, I'm keen on hearing the author's thoughts on how allowing for monotonically changing values for the lambda and or tau parameters over the iterative steps in the analysis can possibly benefit future work of this sort in multiple system estimation applications. One from Christine Chai at Microsoft Corporation. I'm happy to see that advanced statistics has been used to address the problem of modern slavery, and this paper is an excellent example of data science for the public good. I also like that Dr. Silverman published the code and datasets so that the readers have a starting point for the implementation. In the case of counting casualties in armed conflicts, Dr. Silverman pointed out the dark figure as an important part because these victims do not appear on any list. The total population estimate should be the sum of the total number of persons observed and the dark figure. The Poisson distribution is an obvious choice for count data, but Dr. Silverman also includes the interaction terms between the data lists in estimating the dark figure. The correlation between lists is unsurprising because some victims are easier to be found than others. The independence assumption is quite easy to make in statistical models, so I'm impressed that Dr. Silverman investigated in the interaction effects and compared different thresholds for the model. Since the total number of victims observed is the other part of the casualties, I would like to add some resources for record linkage, where multiple records can belong to the same person. Sadowski et al. Applied several blocking methods to partition the casualty dataset from the Syrian conflict in order to reduce the amount of all-to-all comparisons needed. After the dataset is divided into mutually exclusive and jointly exhaustive blocks, only the records within each block are assumed to have a potential link. A probabilistic approach is the locality-sensitive hashing, which assigns similar items to the same blocks with high probability and assigns non-similar items to the same block with low probability. The LSH method allows more flexibility than traditional blocking rules in record linkage, so that we are likely to discover more potential links between the records. Last but not least, quantification of modern slavery requires collaboration across international organisations to get more accurate results. Therefore, I would suggest Dr. Silverman reach out to the HR, Human Rights Data Analysis Group, and other non-profits in a similar field.
know I'm not allowed to respond in the middle of a contribution, but of course...
But you're going to anyway.
If you read acknowledgements, you'll see that I was indeed in contact with them. But that's not... I'll make the point later.
Yeah. Now from Malcolm Faddy, School of Mathematical Science at Queensland University of Technology. I have some comments on the assumption of Poisson distributed counts. Forward selection of interactions after inclusion of all main effects using classical likelihood methods and Poisson log linear modelling leads to the same 6 two-way interactions given in Table 15 for the UK 6 lists data in Table 1, plus one other, ng.go, all being significant. However, using alternative over and under dispersed extended Poisson process models, EPPMs, described in Smith and Faddy, indicates some under-dispersion relative to Poisson. This effect is much smaller if the ng.go interaction is dropped, and if the least significant remaining interaction is also dropped, then some over-dispersion is apparent. So the fitted model with 6 interactions would best conform to an assumption of Poisson residual variation. How crucial, then, is this Poisson assumption for the estimate of the dark count is lower from the model closest to Poisson residual variation compared with that from the model with the extra significant ng.go interaction. Last one from Kuldeep Kumar at Bond University, also in Queensland. I join the chorus that there is a strong need for more research in estimating the victims of heinous crimes such as human trafficking, especially for laying down the foundation for policy implementation. The present study reviews a number of methods and investigates their performance on a range of real data sets. My suggestion to the author would be to utilise the rich data set that they possess for various other research avenues using graph analysis techniques, which include link prediction analysis, clustering and visualisation. These techniques can be used to find suspicious individuals, existing network relationships, unusual changes, anomalous network structure, as well as geospatial dispersions. Beside the visualization of a dynamic and complex data in the form of graphs leads the user to have a detailed overview of the data, filter, select, and look into network details. I'll be personally keen to have a look at the data and use the expertise available to do the same and take advantage of the hard work and commendable efforts put in by the author in the collection and compilation of the data from several sources.
Thank you. Well, you should never get between people and their lunch, dinner, or drinks reception, so I will only respond briefly. I want, first of all, to say that when I used to run discussion paper meetings and so on, the dream paper was one which maybe the paper had all sorts of issues with it, but the discussion it provoked was a good one. And I want to thank you all for what you've said in the discussion, because I think that what you have done will genuinely give future researchers some real meat to chew on, and I can see enormous numbers of really useful projects, PhD theses, and so on coming out of this so people can look at all the details. I only want to make some general points. First of all, several speakers were crying out for more information about the data, not least the last one who wanted to build linkages. My colleague Sarah Henry, who said she would like to see details about breakdowns between sectors. And I can't remember who else it was, Sheila Bird, of course, made the point that you would want to know about the type of victimization. I couldn't agree more. That is a really, really important point. And I think somehow we have to socialize with those who collect data in this area the notion that it really would be in the public interest and in the interest of victims to try and get more detailed, more crunchy information about the individuals, about victims out there. And we need to really all work together. And maybe some of it will involve DNA, which is what Sheila Bird suggested. Maybe it might involve various forms of homomorphic encryption, where you could actually you could encrypt features of data and learn something about them. Of course, the methodological challenges in dealing with such data would mean that you'd need a whole bigger if you're going to use multiple systems or anything like it at all, you would need to look even further into all the issues that people have brought up. But obviously, the sorts of people that are involved in nail bars may not be the same as those in car washes. In general, frankly, men wash cars, women do nails, and that's a simple thing, obviously. And there'll be many, many other examples. Sex work sadly involves both men and women, but they tend to be very young. Cannabis farmers come from particular communities, and so on. So clearly, this is something we need to we need somehow to get more data and more information. I want to thank Helen Ross for standing up and talking about the work that I've been talking about with her already. And I would like I can scarcely commend it because I actually made the point myself to the ONS, but I would commend the idea, and this is something that John Whitehead said. Obviously, another thing to do is if you know what the risk factors are and if you know what the predisposing factors are, you then try and address those directly, you address the causes. But of course, if you wanted to do something about heart disease and lung cancer, you don't just measure the number of smokers. It's a good way of measuring, doing how well you're doing to reduce lung cancer and heart disease, but simply just reducing the number of smokers isn't the answer. I think it's both and rather than either or. There were, as I would have expected and anticipated, a lot of technical contributions, because we love that, don't we? And yes, of course, the methodology I suggest is only a jumping off point for further development. It will cope perfectly well with three list interactions. It's just that I didn't, and I should have maybe. Whether I did or I didn't, and that's therefore a topic for further work. I would gently say to John Whitehead, and I thank him for going into such detail, he fitted all three list interactions and he came out with a figure of 600 for the dark figure. And I think one has to ask, again, if you read George Box on parsimony, he explains why you want a smaller model. And with respect, I would suggest that 600 just isn't a credible result. And in the end, we have to say, I mean, it's not formal use of prior information, but informally, if an approach gives you 600 as a dark figure for the United Kingdom, then maybe it's not, that model isn't to be used in detail. But, you know, it still nevertheless demonstrates the importance of looking beyond what I did and looking at the three list interactions. Well, I think, because I like keeping to time, I'd like to say thank you all again. I will look forward to reading and writing about all the contributions in my response. In the end, however, this isn't about what I should do. This is about what we should do. And any response that I make is not about ways I think my method matters. It's a matter of saying, by bringing this method to light and discussing this method, we expose larger questions that will help all of us in going forward to develop what we should be doing in the future. So thank you all very much for coming. Thank you.